Today I would like to talk about the things that you should connect, and maybe also those that you should think about before connecting. Now that said, I must give you a warning. Where's the clicker? Oh, it's on the podium. Thank you. And the warning is the following. I'm an aerospace engineer. And when I was told that invited to come over here, I was wondering what my first presentation or my first slide should be, and there it is. I show a lot of characteristics with that poor elephant. I'm about as clumsy. I'm about as ignorant about the Internet of Things. And I share a few other characteristics, including the weight. But that said, I started thinking a little more, and I thought, well, since I'm a fraud anyway, I might as well go on and keep pretending. This is an actual and accurate picture of my lab, except that the rocket that has been built over there has already lost its top. Okay, so it's a rocket without the top. But otherwise, it's pretty much the same. So I started recovering a little bit when Alain Louchès from the CDAIT told me, Eric, you should go to this conference. And as I looked over the Internet of Things, I saw that, in fact, in the not so recent past, I share my building with one of the people associated with the Internet of Things early on, named Sanjay Sarma. He was working in the basement of the building. I was working on top of the building. And obviously, he's done a lot better than I did. And you may notice, by the way, that this is one of the MIT buildings that, frankly speaking, look like and still looks like a dump. Okay? So I guess that we both, nevertheless, did pretty good. I had just more sunshine than he did. So I goofed off more. And then, so this is the center with which I work, Center for Development and Application of Internet of Things Technologies. You will notice that if you pronounce the acronym aloud, it's named CDAIT. It's like sleep, sleep. And this is the kind of joke that French people come up with, including Mr. Louchès. What is the Internet of Things? If we go to the definition available on the web, the Internet of Things is a global infrastructure for the information society enabling advanced services by interconnecting physical and virtual things based on existing and evolving interoperable information and communication technologies. Now, as Richard said, my specialty is more like cyber-physical systems. That is, I try to add mass to whatever I deal with. And the mass can be quite enormous, for example, that of an elephant. In cyber-physical systems, the definition, according to the National Science Foundation in the US, is that they are engineered systems that are built from, depend upon the seamless integration of computational algorithm and physical components. Advances in CPS will enable capability, adaptability, scalability, resilience, safety, security, and usability that will far exceed the simple embedded systems. Embedded in what? Embedded in stuff with mass. And the CPS technology will transform the way people interact with engineering systems, just like the Internet has transformed the way people interact with information. So you already see some of a parallel between cyber-physical systems and the Internet of Things. The promise of cyber-physical systems is similar in the sense that it aims at changing our society from the inside out. But before I go and talk again about cyber-physical system, let me just add one thing, which is, in some cases, Internet of Things and cyber-physical systems are considered to be almost the same. So the question is, what can I afford not to connect to the internet? What you're seeing here is LaGuardia Airport in New York. The red stuff are aircraft landing. The green stuff are aircraft waiting to take off. And the fact that we have access to the position of this aircraft on the airport surface is a testimony to the agility of the air transportation system. This information has been available just about the same time as people started talking about the Internet of Things. At least the airlines and the air transportation system is not too far behind. Why can't I live without it? Why can't I afford not to have it? It's because this information allows me to decrease the amount of fuel that is burnt around the airport by aircraft waiting to take off. I can reduce the number of aircraft without changing the airport throughput, and therefore operate in a leaner fashion. In fact, following the prototype that I built, the MIT Lincoln Laboratory has evaluated how much having access to this information can enable in terms of dollars and environmental benefits. Looking at the 7 or 8 major airports in the United States, it concluded that over a period of 20 years, we could save in fuel on the order of about $3 billion. And we could save, in terms of fuel burnt, about 1 million gallons, oh, sorry, 1,000, I think it's a lot more than 1 million gallons, sorry, it's 1 billion gallons that we could save. And therefore, that means 1 billion gallons that don't go into the atmosphere. Okay, there again, significant environmental savings. Why can't I use or live away from, leave my cell phone behind? Because I don't want you to. I can use your cell phone to do a lot of interesting studies of how much time you're going to stay at an airport waiting for your next flight. Guess what airport in the US is where you wait the most? Okay. Somehow, the time you spend in Las Vegas from your last flight and waiting for your next flight is the longest in the country. I'll let you think about why. Having these maps can also allow us, these connection maps can also allow us to get some valuable information about what happens to you during normal times, but also what happens to you during, I don't know, like a sandstorm, for example. And maybe help you recover from the annoying situation of having to spend 1, 2, or 3 nights at the airport instead of getting safely back home. So why I wish I had been connected to the internet during prior studies. Well, one of the studies that we ran was a pilot crash avoidance system. And what you can see is that we had a lot of work that went to this. We had to design our own GPS receiver, our own program, everything to our own computer, and to study how cars can transmit the onset of danger to each other. We had to program a whole car-to-car communication system, allowing those cars, again, to communicate. Of course, the computer together with the wireless receiver, together with the GPS receiver, first of all, was not working all the time. And second, it was weighing a couple of kilos. I think all of it could have held inside today's smartphone had the technology been available back then. Can I afford to connect my drone? This one is a prototype that we flew between 2003 and 2007. We even sold it. And guess what this drone was flying next to? A highway. We were flying just above a highway, and the guys were asking us if we could go even lower in order to see if we could recognize the license plates of the cars that were on this highway in Chicago. Can I afford to connect my drone, and can I afford to operate it? I would say my answer is the same as our Cisco speaker yesterday, which is certainly not. That's where cyber-physical systems meet with the Internet of Things. Okay? It is in what we call the safety-critical applications. And unsurprisingly, these are the ones that I spend most of my time studying now. There are plenty of places where we can think about the Internet of Things playing a role, but we've got to be careful. The kitchen, Mars, you know, we talked about this planet, but I think that human spirit and human genius is already on Mars. Okay, it's already in action right now. And there, of course, there's the little cartoon about the guy undergoing brain surgery and having used 99% of his quota. So what do we do in those cases? Well, we have to be very careful. And we have to be very careful if we are to make the Internet of Things act on physical objects, as opposed to receive information from physical objects. When we act on physical objects, we absolutely have to keep them in check. And what we have is a feedback system where things communicate and act on things in a circular manner. Now, for pure communication, that's not a problem. With my remote control, I can control the channel of the TV where I get my show from, and then if I'm bored, I can switch channels. Okay, it's a nice little feedback system where information moves from one spot to another in a matter of milliseconds. Now, however, that also holds when you drive a car. Okay, the information still goes in a matter of milliseconds between me and the road to come, and maybe the deer that sits on the road. And that is already a more safety-critical situation. Now, how about the Mars case? All right, here's my driver on the left. He's a former student of mine who managed to end up at the Jet Propulsion Lab in Pasadena. The time it takes for my student to communicate with opportunity, or curiosity, to be more precise, is 12.5 minutes on average. The time for information to come back is 12.5 minutes. Now, as you can see, the terrain around Curiosity is anything but flat. So if I want to drive Curiosity on Mars and effectively establish human presence, the human may not look like us, but I think in spirit it is, well, we're going to have to make it even more human in order to prevent accidents. I just can't drive this thing. It has to drive itself. So that by adding autonomy logic, we can have this thing drive itself and the driver concentrate on higher-level things, such as finding a good rock to analyze, detecting quicksand, or detecting rocky areas. These two things being extreme matter of concerns for Curiosity. So that means that, well, another way of saying it is if we're going to go on Mars, we can't help it, but we have to let these things go autonomous and have a life of their own. So cyber-physical systems, we have to treat them with a lot of care, and we have to actually let them go on their own and teach them a lot of tricks if we are to operate them remotely, if we are to operate them from the internet, and nevertheless maintain safety. Think about telesurgery. What that may mean is the following. Maybe the way that things are done today, whereby a surgeon does the exact motion that a robot replicates thousands of miles away, that may not be the right paradigm. If you have a delay, a latency in the system, then you're not going to be able to do the surgery properly. You may even cause damage. Maybe a better way of doing things is act as a supervisor, just like jet aircraft pilots have learned to do over the past 20 years, and just like my Mars robot driver has had to start with anyway, act as a supervisor, not as a direct actor anymore. Let me finish by a note on education and its connection to the Internet of Things. We're dreaming about a system whereby we can teach people all over the planet how to control a little contraption, which is that helicopter-like system. The question is, this is something with real mass, and I guarantee you that if you don't operate it properly, it's going to crash. What should we put between the operator anywhere on the planet and this physical machine in order to make sure that safety is never at stake? Safety is never compromised. This machine is a little bit more complicated than, for example, operating a telescope remotely. Okay? It requires advanced logic. We don't want anybody to screw up that logic or to introduce logic that will make it behave badly. We think we have an approach to do that. Once we are able to make it happen on this, we'll make it happen on a rocket instead to have more fun. But then we're facing another problem, and I want to leave you with that thought, which is, well, anywhere on the planet probably applies less to this beautiful city, but more to areas where people have few means. And that brings us back to Africa. And here's the problem. In order to get the Internet of Things act as part of the educational mission that we have, we probably need to introduce the Internet of Humans in those areas where there is virtually none today. So with that thought, I want to stop my presentation and take your questions.
Well, let me kick off with mine. You talk about decisions that we have to make. We can connect everything, but we've got to make a decision. What should we connect and what should we leave unconnected? And given that aviation, aerospace is your theme, here's my question. Last week, I was at the Boeing factory in Seattle, and the big talking point there was Wi-Fi on aeroplanes. And everyone's very concerned about what if someone hacks into the Wi-Fi and somehow can hack into the control system of the aeroplane, and that's a doomsday scenario. Whenever we're talking about aerospace, whether it's a drone, whether it's a commercial aircraft, whether it's space, the potential for it to be hijacked in some way is terrifying to us all.
Yes, absolutely. Aerospace is sort of the poster child of bad news. And you know that this problem has occurred and that a scientist in the US has been indicted for having broken into an A320 and a 737 aircraft vital control system, probably not from the entertainment system, but through one of the numerous plugs that you will see under your seat. Just take a look next time you fly. So this is not a question. This is, by all means, reality. Things are going to get even more challenging when we start communicating on a daily basis, on a minute-by-minute basis with the ground, I mean the back of the airplane, the information that's going to go through a router down to the ground will share that router with the critical flight control system. How do you make sure that whatever you're talking about or typing in from the back of the aircraft will not make its way to the wrong place? So yes, this is a very important question, which needs to be weighted against the tremendous economic advantages that you get out of sharing resources as far as information system and other systems go in aviation. The lighter, the better.
In fact, one of our speakers in the next panel session says, we have to get used to living in an unsecure world. Deal with it. This idea that we can have absolute security is a fallacy. And I guess then it's your case of how secure do we want to be?
So in the case of aviation, the problem is that it has been a little too good. The chances of running into a problem today, I mean, basically dying, are 1 chance per 1 trillion per hour. So it's very, very, very small. It would take hundreds of years of flying for you to have a high probability of getting, well, basically destroyed. So we've been spoiled. We've been spoiled of these beautiful aerospace engineers who sort of worked very hard to make flying maybe part of our nature. Now, when it comes to introducing new technologies, it's harder. It's harder because while aviation evolved from iffy beginnings, I wouldn't want to fly in the Wright brothers aircraft, and has slowly evolved to becoming the safest system in the world, the safest transportation system in the world. Innovation today doesn't have that luxury. It must work right first time. Can we do that? That's where your question becomes very pertinent. Should we allow a little bit of risk when we introduce new technologies? Or should we keep flying in the venerable 707 or even the de Havilland Comet?
I'll take one more question for the good doctor. Yes, please, a question here.
Do you think government facilities should be connected to the internet, considering the large margin of error in concerns with security?
So it's not a matter of whether it should be connected. I mean, they are already connected. The question is, how do we make sure that we have the proper security in place so that break-ins cannot happen? And as you know, this is a very interesting race that hackers run against security developers. And just like police and gangsters, you wonder which is which because they look so much alike.
Very quick final question.
Sure, quick question. My name is Nabil Nawaz. I run a consulting integration firm. We look at programmable data centers. Thank you, Dr. Feron, for your presentation. You mentioned this concept of when you're talking about the Mars rover and it actually going around and trying to figure out, because of such a long delay in sending and communicating with it, you mentioned this concept of autonomy logic. And I presume it means that it has to figure out itself what to do in certain situations. It sounds like that's something that can be very much applicable to many other things. Could you just expand on that concept of autonomy logic?
So, in Spirit, the autonomy logic, well, we'd like it to be as smart as a human, but we would like it to be as little failure prone as possible, and that is not a human characteristic. So the kind of autonomy logic that we're talking about here is human genius with under heavy checks, okay? Under a lot of verification. We are trying to make a verifiable human being that is as smart, but a lot safer. Of course, this could apply not only to the Mars rover, but it already applies to the Google car. how many of you know that the head of artificial intelligence at NASA quickly became the chief scientist of Google? Well, such is what happens, okay? Technology moves from one field to the other. And you can probably say that a little bit of the Google car came from Mars.
Fascinating insights. Dr. Eric Feron, it's been a pleasure having you in Dubai. Thank you very much indeed for joining us today.